applications of linear systems is where we see the real life use of these systems. Businesses and planners like that, they use this a lot more than you probably realize in the behind the scenes work. So our target is that we can choose the best method for solving real life situations that involve systems of linear equations. Over the past 3 lessons, you've looked at 3 different methods for solving systems. The first one you looked at was graphing. This is where both equations must be written in slope-intercept form as y equals mx plus b. If they weren't already given like that, then you have to manipulate it to get y isolated. You graph both these lines, you see where they meet, then the intersection is the solution. This is the easiest one if you have a graphing calculator and it's easy, or the lines are already written in the form of y equals mx plus b. Substitution, this is the one that you probably will lean to the most. It's where you single out an x or a y. You have your blobs, your blobs, and then you substitute in for the other one. You make sure that one of the variables is isolated and you substitute it into the other equation. Solve it, and then repeat that process, plugging it in to find the other variable. And then last we saw elimination. That's where you line them up, you look for the matching coefficients, and then you add or you subtract them to eliminate those. So let's look at something called a break-even point for a business. And so the break-even point, that is where your income, how much money you are bringing into the business, equals your expenses. Some businesses don't plan very well and they show a loss where they're spending more to create whatever it is that they're selling or offering than they're bringing in. So you want to at least be able to break even. So our boy Gavin, he is making those Altoid cell phone chargers. His initial cost for the tools, let's say they're $20, like the screwdriver and whatever else the tools are that he needs. The supplies for each charger, the tin, the battery, the cords, all that, is $15. The price of the charger is $20, so that's what he's selling them to somebody else. So what he's wanting to know is how many chargers must he sell in order to break even. Let's get a pen. Okay, so first, let's write an equation for his expenses. Expenses, that's what it's costing him to create those. So we got to define our variables too here. Y is the dollar amount, and X is the number of chargers. How many chargers is it that he's creating, or the number of chargers that he is selling? So for his expenses are equal to, he has an initial startup cost of $20. That's to buy his tools. He can reuse those tools with each charger. Plus, it's costing him $15 per charger. So that would be 15x. So that's the cost for his expenses. Now let's write in an income equation. The money that he's bringing in is $20 per charger. $20 times however many chargers he sells. So now we need to solve the system. We need to decide which of these 3 methods that we looked at would be the easiest. Right now I don't have a graphing calculator in front of me, so I'm going to bypass the graphing method. If you have one in front of you, you may think it's pretty easy to plug those in and then look where it intersects. I'm going to choose substitution. Okay, so since we have y isolated, I'm going to take 20x and I'm going to substitute that in for y. So my super equation is 20x equals 20 plus 15x. I need to reunite my variables. I'm going to move the lesser coefficient, which is 15x. When I subtract 15x on both sides, I'm left with 5x equals 20. Divide both sides by 5. X equals 4. So in order for those two things to be equal, the number of chargers that he needs to sell is 4 chargers. If he sells less than 4 chargers, he is spending more money than he's making. If he sells exactly 4 chargers, he's broke even. After 4 chargers, the 5th, the 6th, the 7th charger that he sells, that is where he starts to turn a profit. Another way that systems are used is when you are identifying constraints, like limitations on something, and then looking for a viable solution. Now, viable solutions, those are the solutions that make sense in real life situations. So let's go back to our example over here. If I had gotten that x equals -2, for instance, Gavin's not going to sell -2 chargers. That's not a viable solution. And so what that would mean is that if -2 was the solution, that means he would never break even, is how that would be applied in real life. So let's look at this second example. Staley Farms, it has some leaking water tanks. One of the water tanks contains 10 gallons of water, and it is leaking at a constant rate of 2 gallons per hour. The second tank contains 6 gallons of water, and it is also leaking at a constant rate of 4 gallons per hour. When will the tanks have the same amount of water? So I need to decide what my y value is and what my x value is. Y is going to be gallons in the tank. That is my dependent variable. My dependent variable depends on x, which is the hours that it is leaking. I can see how much water is the tank based on how many hours it's been leaking. So I need to write an equation for each tank. So for tank 1, that equation would be y equals, it is starting with 10 gallons of water. It contains 10 gallons of water, but it's leaking, and if it's leaking, it's losing water, which means that's being reduced. I'm going to subtract 2 gallons for every hour. That's tank number 1. Then tank number 2, its equation would be y equals, it's starting with 6 gallons of water, and it is also losing water at a rate of 4 gallons per hour. So I have my equation for each tank. Now I'm ready to solve that system. So if I have a graph, again, that would probably be easiest to graph it. I don't have a graphing calculator in front of me, so I could do substitution. One of my y's is already isolated. Elimination is not going to work very well for this one because they're not in standard form. If they were, you know, that would be very quickly. I could do that very quickly, and you could even change it to standard form if you like elimination. One of the beauties of systems is there's lots of ways to do it, and you get to choose your personal preference. I'm going to choose substitution. I'm going to put 10x in for the y over here, substituting that in. So my super equation is going to be 10 minus 2x equals 6 minus 4x. To solve that equation, I'm going to move the lesser coefficient, which is -4x. I move it by adding 4x to both sides. Once I do that, I get 10 plus 2x equals 6 comes down. These cancel. Then I'm going to subtract 10 on both sides. I get 2x equals -4. So the point where those two will be equal, the x value, which is hours leaking, -4 divided by 2 will be -2. So I have to ask myself, is this a viable solution? X is representing hours leaking. Can something leak for -2 hours? No. So the solution, yes, it's going to be -2. The other coordinate, if I put -2 into that, if I put -2 times 2 here is -4. 10 minus -4 will be 14. That's the solution to the system, but it's not a viable solution. So what that tells me is that the tanks will never have the same amount of water. So let's go over what just happened, because a lot is happening here. That's my actual answer. The question is asking, when will the tanks have the same amount of water? So we used a system of equations to figure that out. The solution to the system is negative 214. I know that because I got that x equals negative 2. Put negative 2 back in here. 10 minus 2 times negative 2 gives me 14. So the system has the solution negative 214. If we had no context to this, if I'd never mentioned water tanks, I had just given you two equations, you would have written down that the solution was negative 214. But as we're applying it to real life, we have to make sure that those solutions are viable, that they make sense. So put the context with it. Negative 2 hours leaking, that doesn't happen. So what that tells me is that the tanks will never have the same amount of water. It means that there's not really a true solution to this equation.